Okay, you guys, so welcome again. Here is where we left off in class for some of you, depending on which class you were in. And what we had looked at were Taylor series, and we were looking at how to construct a Taylor series for things like sine, cosine, e to the x, transcendental functions that you cannot use Big Mama. Remember, Big Mama was 1 over 1 minus x, and then we generated all kinds of series by substituting stuff in for x. And intervals of convergence were -1 to 1 unless that coefficient was other than 1. My kitty's trying to help. I had to get her off. Okay, so this first example, it says example 2, but it's secretly just example 1 for you guys. It substituted x to the third in for x for sine. And these ones you know, or you will know, by the time the AP rolls around. So all you're doing is substituting in x cubed, keep on going, keep on going, keep on going, write the general term, and you're done. So I just simplified. And again, these are the ones that you have to memorize. You gotta know these for the AP, including the intervals of convergence. So you have to know what's going on with that. So we can use the same idea. I'll do this one out just so that you see it one more time. If I've got cosine x, that is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, and it alternates, minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial, etc. until you get to the general term, which is -1 to the n, so that it alternates, x to the 2n, we got to make sure that they're even, all over 2n factorial. Okay, so that is my general equation, and it's a Maclaurin series because it's all centered at 0. So here we've got square root of 2x, so all I do is substitute that in. So cosine square root of 2x, it's still going to start with 1 because there's no x to substitute, minus square root of 2x squared, got the factorial down there, plus square root of 2x to the 4th over 4 factorial minus square root of 2x to the 6th over 6 factorial plus square root of 2x to the 8th over 8 factorial. Now on the multiple choice you won't see it written like that. They will have simplified to, let's see, they will have simplified it to 1 minus 2x over 2 factorial plus 4x squared over 4 factorial. So all they're doing is raising those square roots to powers. This is going to be 8x to the 3rd over 6 factorial plus blah blah blah. So I'm substituting square root of 2x. So I'm still going to have the sum. It's still going to be going from 0 to infinity. It's alternating. I've got the square root of 2x to the 2n all over 2n factorial. And if you think about the square root of 2x being 2x to the 1/2 raised to the 2n, then I'm multiplying those exponents, so 2n. It's going to cancel this, and I'm just going to get 2x to the n, the parentheses are important, over 2n factorial. Got to make it alternate. Stick that on the top, though it can just be out front. And I'm going from 0 to infinity. Done. Done, done. All done. So these work the same way. I'm not going to go through this. You write out e to the x, substitute x squared, write out sine x, substitute x over 2. So those ones are fairly simple, but this one, most likely people would write out sine x and then they would square it. And you can't do that. You cannot square a series. So I want to make a big deal out of this. It's tempting, but you can't. We have to make it into something that you have the original and then you're substituting. So this identity, which you learned in your early childhood math, that would be last year pre-calculus, is the double angle formula for cosine, which comes from sine squared. So you have to know things like that. So I'm going to rewrite this. Sine squared x is 1/2 times, just kidding, actually, yeah, 1/2. I'm going to have cosine 2x over 2. So I'm going to be substituting 2x in to my cosine series, dividing it by 2. So I'll always have a 2 on the bottom plus whatever factorial is there. So that's going to be, let's see, 1/2 minus, so cosine of 2x, and then remember cosine is just 1 plus x squared over 2. So let's see, this is going to be 2x squared over 2 times 2 factorial plus, now I just realized that we're going to have to be distributing this negative through. So that minus is going to change my signs. So let me do this. I think I'm going to write it a little bit differently. So before I do all of this, I think I'm just going to write it a little bit differently so it's clear what in the heck is going on. So I have 1/2 minus, let's see, 1/2, and I'm just going to substitute 2x in for cosine. So it's going to be 1 minus 2x squared over 2 factorial plus 2x to the 4th over 4 factorial minus 2x to the 6th over 6 factorial plus, that's supposed to be a 6, kind of hard to see that, 2x to the 8th over 8 factorial, etc. And then I'm going to distribute my 1/2. So distribute that to everybody, etc. So I've got 1/2 minus 1/2, and then I've got 4x squared. Let's see how this works. Where am I? Okay, so I'm going to have minus 4x squared over 2 factorial times 2, because remember I'm distributing that through, plus 16x to the 4th over 2 times 4 factorial minus, and I believe the next one is 128, 2 to the 6th, x to the 6th over 6 factorial plus blah, blah, blah. Keep on going. And so if I'm doing that in general, I'm going to have 1/2 minus 1/2 times the sum from 0 to infinity of -1 to the n, 2x to the 2n, all over 2 times 2n factorial. Okay. And then I can put, and this 2, it's not down there yet because I stuck a 1/2 out there, so let me not do this yet. And then we'll check the first term. So that's an important thing. Check to make sure the first term really does work. We did it a little bit differently, I think, in my first period, and so we had to adjust the exponents. But this will be 1/2 minus the sum from, whoop, that's supposed to be an equal 0 to infinity of -1 to the n, 2x to the 2n, all over 2 times 2n factorial. And let's just check to make sure the first term works. So 1/2, of course, is going to work. Minus, if I put a 0 in for this, I'm going to have -1 to the 0, 2x to the 0 over 2 times 0 factorial. So that's going to be 1/2 minus 1 over 2. So that gave me my first term. If I put 1 in there, hopefully I'm going to get the correct thing. So I'm going to have minus, so now this is -1, I'll say plus, but -1 to the first, 2x squared. Again, I'm just checking this to make sure that it does work. 2 times 1 factorial, which indeed gives me this term. So I've got the 1/2 that I started with. That's this guy, which is this guy. And then my next term is 1/2. And then my third term is going to indeed give me that. So we're on the right track. We're good. When we did it in first period, I think what happened is we canceled the first 2 terms, the 1/2 and the -1/2. So this right here. And then we had to adjust this formula. So either way you do it, there are several different ways that you can do this so that you get the first term, but just check. Make sure you really are getting the first term. Sometimes I do 2 or 3 terms like I did here. Okay? So let's move to example 7. Big time, interesting example, because we're calculating an error smaller than 0.01. You might say, well, we're in Taylor series land. I don't know how to do error for Taylor series. Well, let's take a look at this. We're integrating between 0 and 1. So let's write out the series first. So I'm going to start with e to the x, and e to the x is 1 plus x squared over 2 factorial plus x to the third over 3 factorial plus x to the fourth over 4 factorial. And I'm not going to write down the general term because we're integrating for real. We're not just writing the squished form plus c. 5 factorial, x to the 6th over 6 factorial plus etc. And this goes with the example above, so I'll mark that off. And in this case, I'm substituting in -x squared. So here we go. E to the -x squared is 1 plus -x squared plus -x squared squared. Got the factorial in the bottom, plus -x squared squared to the 4th. Got the 4 factorial still on the bottom, and -x squared to the 5th over 5 factorial plus -x squared to the 6th over 6 factorial. Seems to be a little lag in this thing. Plus blah, blah, blah. So let's just simplify it so you can see what's going on. I got e to the -x squared equals 1 minus 2, just x squared, plus x to the 4th over 4 factorial. Now, did I skip one? I sure did. Look at that. This should be 3. This should be 4. This should be 5. I could have put a 6th one on there. Okay, let me continue. So this is going to be minus x to the 6th over 4 factorial. Nope, it's not. This was 2 factorial. Holy cow. Cows are holy, aren't they? I'm getting ahead of myself here. All right. So this was x to the 4th over 2 factorial. And let me get rid of this little guy too. Kind of looks like I'm adding things. Okay. So I've got minus x to the 6th over 4 factorial plus x to the 8th over 5 factorial. And then I'm going to have a minus x to the 10th over 6 factorial. And you keep on going. Notice that this is an alternating series. We know how to find error for alternating series, right? These guys are changing sign at every step. So remember, all I do to find alternating series error, and I'm looking for something that's smaller than 0.01, is I substitute, right? So I substitute, in this case, 1. And why am I substituting 1? Because I forgot to integrate. I forgot that we're integrating. We're not there yet. Okay, we're going from 0 to 1. So this now, and I'm just going to blow through example 8. We will do that. I'll just do it on a separate page. So when I integrate this term by term, it's x minus x cubed over 3 plus x to the 5th over 5 times 2 factorial minus x to the 7th over 7 times 4 factorial. And this is the advantage to actually writing these out instead of just trying to do it in squished form. X to the 7th. Did I just do that? I did. I meant x to the 9th. Okay, let's grab a pen again. So this is 9 over 9 times 4. Just kidding. 5 factorial minus x to the 11th over 11 times 6 factorial, etc. Okay, that's the integral. Now I'm integrating between 0 and 1. I don't really know what that is, but I can find the error. Remember, when I substitute using the fundamental theorem of calculus, when I put the 1 in there, that's going to generate actual numbers. If I put a 0 in there, that's going to be 0. So when I do the 1 minus 0, the whole second part lops off, which is convenient. So now, and this is the reason, now I put the top limit in, and I'm just going to evaluate. I'm not going to evaluate. I'm just going to look at the terms. So 1 over, and I won't even put the plus and minus sign in there. We'll put that in just a second. So what we're looking for is a term that's smaller than 0.001. Clearly 1 does not work, and neither does 1/3. So we just keep on going, evaluating the heck out of these. This one is going to give me 1/10. Clearly that's 0.1, that's too big. This guy's going to give me 1 over 42, which looks kind of promising, but it's 0.023. Still too big. I'm trying to get smaller than 0.01. And 0.02 is bigger than 0.01. Keep on going. This one is going to give me, if I just throw it in a calculator, 0.00462. Well, that is a very happy thing. That's smaller than 0.01. It's the first one that's smaller. Now, the alternating series error says once you find that term, you cut it off, and I'm going to add the first 4 terms. And here's where the signs become important, because I'm really adding 1 minus 1/3 plus 1/10 minus 1 over 42. And if I do that, I get, what is it? I get something very exciting. 0.742. And I'm going to write all of these out, and I suggest that you do that. 857,149. Now, if I change my strategy and I say, hey, I'm just going to use Mr. Calculator Man, he will very happily give you a value that's really similar, actually. So he's going to experience success in just a minute, which is why he's smiling. Calculator Man, kind of an ugly one this time. No, not ugly. Okay. Which is 0.746. Look at that. 824. 1328. So if we round this, so it's going to be 0.743, 0.747. We're going to get an error if you actually subtract this. Between the calculator's estimation and my estimation is 0.003, 966, 99. Okay, now remember, this is still an approximation. I don't really know. I mean, the calculator's doing the best it can with however many terms it's busting out. All we did was add 4 terms. Wow. So that is a big wow. Calculator Man says, wow. Okay, so, and I know there was one on the AP a couple of years back where it looked like you were going to have to use a different type of error, but then it wound up being an alternating series, and that's very simple to calculate the error versus what I'll show you with Taylor series error, which is a little bit more complex. Okay, last example. I'm going to pull up a brand new page because the last example is showing that e to the I pi plus 1 is equal to 0. So that would suggest that e to the I pi must equal -1. And this is a question I've gotten. I don't know, people look at this in books and go, how is e to the I pi -1? So let's try it out. So e to the I pi, let's see, e to the I pi, and I'm just taking the e to the x and I'm going to substitute I pi in there. So I'm going to get 1 plus I pi plus I pi squared over 2 factorial. Then I'm going to get I pi to the third over 3 factorial. And I'm going to write out enough of these so that you can understand what in the world I'm doing. Plus I pi to the 4th over 4 factorial plus I pi to the 5th over 5 factorial plus I pi to the 6th over 6 factorial. And I'm going to try to squish one more in there. I'll squish in I pi to the 7th over 7 factorial. And you can see that pattern just keeps on going. Okay, so if I simplify that, e to the I pi equals 1 plus I pi. Now remember, when I square I get -1, right? So I'm going to have negative pi squared over 2 factorial. I'm going to have another minus I pi to the 3rd over 3 factorial, remembering that I cubed is -I. So this is why you had to know that pattern. This one's just going to give me pi to the 4th over 4 factorial because I to the 4th is 1. And then I'm going to get plus I pi to the 5th over 5 factorial. So these repeat in patterns of 4, which is why you still had the I there, minus just plain old pi to the 6th over 6 factorial plus blah, 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 keep on going. Now, imaginary numbers are imaginary. We are in the land of real numbers. This is going to cancel. And then we can reorganize this. So I've got e to the I pi equals 1 minus pi squared over 2 factorial And I'm going to pick all the even ones. Pi to the 4th over 4 factorial, and then minus pi to the 6th over 6 factorial, plus, and then for the odd ones, blah, 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 I'm going to pull out the I. So I'm going to get pi minus pi to the 3rd over 3 factorial plus pi to the 5th over 5 factorial plus, keep on going with that one. Now hopefully you recognize what this is. This is cosine, right? Even powers. So what this is just cosine of pi. It was cosine x where we substituted in pi plus, and then I've got I times, hopefully you recognize, oh my goodness, that is sine pi for the same reason. Okay, so you recognize these powers and it starts with 1. You got this guy started with x, so instead of x I have pi, and then I've got odd powers. Odd powers is sine. Well, cosine of pi, you know, is -1. I sine pi, well, sine pi is 0. So I'm saying -1 plus 0 is -1, which is why e to the I pi is -1. Crazy. Which means the original question, which was e to the I pi plus 1 equals 0, works. Okay, so most people come up to me and say, hey, why is this true? And I say, well, it's a long story. But here we had an example that required you to prove that, which is way exciting, way exciting. So let me just peek at where we are. I think the next page is a homework page. Why, yes, it is. So I'll be posting answers for that. And then we'll continue. There's a Taylor series error, which starts here. It's called the Lagrange error. And we'll talk about how do you find error for a Taylor, because it's not the same as for alternating, unless it just happens to be alternating like the one we did. Okay, so I will see you on the flip side with a little error for Taylor. Have a fun day.